Now, we have almost finished the revision of, let's say, undergraduate probability, and now we want to go a bit advanced, and we want to start to talk about random variables. Now, let's do a definition of what a random variable is. Random variables are basically functions that we are assigning them to some random events. So there exist some random events, like you are tossing a coin, and we have head and tail, right? And within this head and tail, we have some non-number terms which are our outcomes, right? So what we want to do, we want to represent them with number, because we can handle numbers much better. So the definition is a random variable, RV means random variable, is a function that is associated, that associates a real number with each element in the sample space. Now, and we have very important notations from now. We will keep following it, and you have to be careful in the exam. And the notation is this: capital letter such as X, and I put these lines in order to represent that this is capital, because my lowercase and capital case X are usually the same, denotes a random variable and its corresponding a small letter, say lowercase x, denotes one of its variables. So capital X can be, let's say, having head in tossing a coin, and lowercase x equal to 1 means that we have one head. So I mean, we will write a few examples so you understand what we mean by capital letter represent random variable, and by what is one of the variables. And the example one is x is a random variable representing number of defective products when 3 products are produced. So we can have a table like this, and this is the outcome produced. And lowercase x is the value of x. Now, let's say D is defective and N is non-defective, okay? So if I am producing 3 products, what are the situations regarding to having something defective or non-defective? It can be all non-defective, right? It can be all non-defective. It can be non-defective, non-defective, defective. Then it can be non-defective, defective, non-defective. Non-defective, defective, defective. Defective, non-defective, non-defective. Defective, non-defective, defective. Defective, defective, non-defective, defective, 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 right? So, capital X tells us it's a random variable. It shows how many defectives we have. And lower x is telling us in this current situation how many defectives we have. So here, what is the lower x? What's the lower x?
0.
0. We have no defectives. What about here? 1. 1, 2, 1, 2, 2, 3. Right? These are the numbers that we have. If the sample space contains finite number of possibilities, like in example 1, we call it discrete random variable. This random variable is a discrete random variable. Because it has a discrete sample space, right? Let's do another example. Y is a random variable representing number of tests that, well, let's say number of questions I changed again, number of yes/no questions that we have to answer till we get no answer. So I have a series of questions which the answer is yes or no, and the random variable tells me how many questions I have to answer till the answer is actually no. Now, what is the sample space in here?
Maybe numbers starting from 0 to...
Yeah, I mean, I can answer one question till I get 0, then I can answer 2 questions, and so on. In other words, it can be like directly no, or it can be first question yes, then no. Maybe the first 2 questions are yes, then no. Then maybe the first 3 questions are yes, and then no. And it continues like that. So I may need to answer 1 question, 2 question, 3 question, 4 question till till it's unending. I can have infinitely many yes questions. If the sample space is unending but integer, like this example that we have, then it is still discrete. In other words, we can count the number, I mean it's countable numbers by discrete. So we have done two examples of random variables which are discrete, so it's very easy to guess that if we are dividing it into the discrete, then it has to be also continuous. So let's see what is the example for a continuous random variable. Z is the height in centimeters in centimeter of random people. Knowing that minimum, it's cool to have background music. Knowing that the minimum height is, I don't know, let's say 140 centimeter, and maximum is 240. Oh, sorry. 240 centimeter. Let's assume we know that our height is limited into this, and we want to see in here what is the outcome, or in other words, if we want to make a table like this, what are the numbers that we have? Now what is our answer? It can be any number. Z, okay, this is capital Z. Z belongs to this range, and it can be any number. In other words, it can be, or it can be this. So it can be any number. Hence, Z, the random variable Z, is a continuous random variable. However, we will focus a lot on discrete ones, and we do lots of examples on the discrete situation. The question about the height is always a philosophical question, because we can say that we have countable number of heights. In a sense that we have 7 billion people on the earth, it means we have 7 billion height. We don't have any different values apart from that, which means we can count it. But this is something that you can go to a loop of infinity. We consider height as a continuous random variable because it can has any value in general. Now, the question, let's do an example. Another example. So we understand what is a discrete random variable, what is a random variable, what is the aim of random variables. Now let's do an example and do a few calculations because we want to come to some very useful conclusion. And the example is that let x be, let random variable x be the random variable representing number of heads in 3 tosses of a fair coin. So we have a fair cone and we toss it 3 times, and our random variable x is representing how many heads we have. So this is our sample space. Which you know that we have 8 possibilities, right? And you tell me, what is x? 0? Or is it 3? 3, 2, 2, 1, 2, 1, 1, 0. Now, we are introducing a new notation. And this new notation is this. P of x is equal to x. P of x is equal to x. And we read it in this form. The probability that the random variable x is equal to this number, which is our lowercase x. In other words, what is the probability that x is equal to 3? Which I'm sure you can tell me. What is the probability that x is equal to 3? 1? 1 over 8. 1 over 8. And we can fill the rest. But in order to fill the rest, maybe it will make much more sense if we write down x, and we write down the probability of x is equal to x. And you tell me what are the values of 3, x is 3, 2, 1, 0, right? So, this one is 1 over 8. Each of one single event is 3 over 8, right? No, it's 1 over 8. So how many 2's do we have? 1, 2, 3. So this one was 1 over 8. This is 3 over 8. How many 1's we have? 1, 2, 3. So this is also 3 over 8. And how many 0's we have? It's 1 over 8. Right? Now, when we have a discrete random variable, because it's a function, so we can represent it by using a terminology which is called PMF, probability mass function. And we want to see what it is, what is its properties, like here, how we can calculate it, and how it can be very beneficial for us. And this is a definition. Fx is a probability mass function known as PMF. You may remember that we have PDF for continuous forms. Maybe in the previous levels you have seen it. So probability mass function for the discrete random variable x, if for each possible outcome, we have these three conditions which need to be satisfied. The first one is, we know that the probability should be positive. The addition of all the probabilities is 1, and the probability of the random variable x is equal to x is actually f of x. Is f of x. So if random variable x has n members, in other words, x is x1 till xn, like in here where we have 4 members, then we can say that fxi is always greater or equal than 0. We can say that the summation I from 1 to n of fxi is equal to 1, and the probability of x is equal to xi is f of xi. And let's do one numerical example. Which in this numerical example we need to remember the formula for combination. And the example is this. X is a random variable representing number of bits equal to 1 in an 8-bit random binary numbers. Find an expression for the PMF. So we want to find an expression for this PMF. Tell me, what are the possible values for x? What are the possible values, Ozan, for random variable x?
2008.
2000?
2 power to 8.
2 to the power 8. But what is x? What is x in English? What is it? What does it show? What does it show? Egils? What does x shows, Thomas? Sorry?
0 and 1.
What does x shows? Come on, don't you read the question. What does x shows? Simon.
Number of bits.
Number of bits which are 1. Number of bits which are 1. In other words, how many bits are 1? So what are the values for x? How many bits do we have in total?
8.
8 bits. So how many ones can I have?
8.
Maximum 8. I can have nose ones, 1, 1, 2, 1, 3 ones, and so on. So the values here are 0, 1 to 8, right? So, what is the probability that x is equal to 0? In other words, what is the probability to have no ones at all? 1 over?
1 over 200.
Yes, 1 over 256. This is the place that we have to consider how many positions we have. 1 over 256. Why? Because we have 8 positions, so 2 to the power 8 is all the alternatives that we can have. But the probability of x is equal to 0 means that here it should be 0. And we have only one situation for that. Right? Now, the probability of x is equal to 1. What is the probability of x is equal to 1? In other words, how many forms can I have for having only one inside this 8-bit?
8 over 2 and 8 over 2.
No, don't tell me the probability. How many forms can I have 1 inside this 8-bit? 8 different forms, because it can be either here, or it can be in here, or it can be in here, and so on. So I have 8 forms, so the probability is 8 over 256. Now, how can I calculate, how this 8 comes from? I have the combination of 8, and I have only one position to be 1. So in other words, if I want to see what is the probability of x to be 2, I have to have the combination of 8 and 2 over 256. How can I calculate the combination of 8 over 2? It's 8 factorial divided by 6 factorial multiplied by 2 factorial, right? And if you do it, you will get what? 28. Right? And what about this one? This is the combination of 8 and 0, which means 8 factorial divided by 8 factorial multiplied by 0 factorial, which is 1. And I am sure that you remember n combination by m is n factorial divided by n factorial multiplied by n minus m factorial. So this is the formula. Now, what about 8? How many ways can I have all the bits to be 1? Only one way. And we know that this 1 is also a result of this, the combination of 8 over 8. Now, who can tell me what is the probability of x is equal to x? The probability of x is equal to 0 is combination of 8 over 0 divided by 256. Probability of x is equal to 1 is the combination of 8 over 1 divided by 256. So what is the probability of x is equal to x? Yes?
What is the combination?
Combination of
n, it's combination x. X
8 combination x divided by
256.
256, or 2 to the power 8. So, and this is our fx. Why this is our fx? We have to check the 3 conditions that we have in here. Condition 1. Combination is always positive. So this is always greater or equal to 0 because positive divided by positive is always positive, right? The second one, the summation of fx means that the summation of this term, x from 0 to a, which is and from the statistic you may know that the summation n from 0 to, I from 0 to n of c and I is what? It's the total number of combinations to the power n. Right? And number 3 is so keeping this example, let's add one more part to this example, because by that we want to define some new terminology. And the continuation of the example is this. What is the probability that there are at most 3 bits on? 3 bits on, we remember that on means 1, off means 0, right? On means bit is equal to 1. So what it asks is this: what is the probability of x, a random variable x, which it is at most 3? And what is the meaning of at most 3? It means that it can be 0, it can be 1, it can be 2, it can be 3. It's at most 3. So it is the probability of x less than and equal to 3, which, because it is a discrete term, it's probability of x is equal to 0 plus the probability of x is equal to 1 plus the probability of x is equal to 2 plus the probability of x is equal to 3, which is equal to summation of x from 0 to 3 and probability of variable x is equal to x. Right? And you can put the values and calculate them and see what is the result. However, this example helps us to define a new definition, which we stop by end of this definition. The cumulative distribution function known as CDF, and we show it by capital F of x of a discrete random variable, capital X, with PMF of fx is defined as f of x is the probability of random variable x is less than equal to x, which is the summation of I starting from 0 to x of f x, or you don't know if the first one is 0 or not, so let's do this one. Summation over x of this. Like in here, we have actually calculated this cumulative distribution function for value 3. Now, this CDF is very important. We use it quite a lot. I mean, those of you who are taking the image processing, you saw that we use it for histogram localization, for instance. It has very important properties, which we will benefit from those properties, but we will talk about those properties next week. I have a meeting, I have to go, so that's why we terminate the class very early today.